and he has 11 chapters of scientific books, 24 scientific publications in international journals, 127 conference papers in international congresses, and 6 patents. He's the co-author of a worldwide patent on a method of manufacturing a bulletproof composite. He was awarded a research grant from European Defense Agency, French Army delegation, financial support, and many industrial partners. Dr. Boussu, thank you.
Hello. 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 You can hear me? You can hear me? Okay, thank you. Thank you, Mr. Chairman, for this very nice introduction. As I understand the previous lecture, I should say that all these scientific results are due to my team, and thank you for them, of course. I would like to thank all the organizers, also the team, as I understand, and especially Arvind Sincha for inviting me and to join me, to this very nice conference. The good thing is the fact that we spoke about a little bit scientific results, just 2 slides on the course because I'm a professor, as you know, but I will skip away very briefly to the applications of that kind of research, especially for research coming from European project. I will talk about that. Unfortunately for you, my talk will be in English with my French accent. Sorry for that. So what I would like to say is the fact that we are talking about 3D warp interlock. Just a few slides about where we are. We are located in the north France, close to Paris, Brussels, London, Amsterdam, and so on. And this is a view of the main entrance of our institute, so you are warmly welcome to see us. It will be a pleasure. I'm a professor in this textile engineer school that is have a very long past, and we are also doing research. All the research activities are available on the website, so please do not hesitate to have a look at that. My plan of my talk will be first to be sure that I give you the right definition of 3D warp interlock fabric, and secondly, we spoke about the application of that kind of structure. So, if I'm referring about 3D warp interlock fabrics, you have 4 main parameters to define these 3D warp interlock fabrics. The first one are the surface yarn. These are, so in green, on the top, on the bottom, it's the they are the surface warp yarns. And in the circular, you can see on the picture, the circular plots are represented the weft yarns. So the first parameters are surface warp yarns. They are only there for aesthetic aspect. The second, the red circular are represented with weft yarns. The third parameter is the stuffer yarns. It means that they are located in different layers of weft yarns. And the last, but not the least, the fourth, they are the linking warp yarns. It means that I should say that 3D warp interlock could be seen as a stack of different 2D layers linking by only one warp yarn, only one type of warp yarns, which is called the linking yarns. It means that for that kind of definition, if it's called a 3D warp interlock, it means that it will be linked in the warp directions only. So if you are interested about that, I have recently published a new general definition of that kind of structure, and you can see that on Composite Part B journal. Okay, just to have a look on that kind of different 3D fabrics and 3D different textile architecture, you can see that there are different axes and different dimensions. and to be sure to where located this kind of structure, you can see that the 3D warp interlock could be represented at multiply with a biaxial structure, but giving a 3D structure. Okay, that will be enough for the course. Now, let's move on the 3D fabrics as fibrous reinforcement for transportation applications. What I would like to say about these results, in fact, they are coming from funds, of course, and funds coming from European Commission. It was a FP7 project, and what is very fair and what is very nice in this kind of fundings, and probably also for the next edition of European funding, is the fact that at the beginning of the project, we are involved in industrial partners, and so it is a mix of academic and industrials. And at the very beginning of the project, we have to write what will be the business of these applications. It means that all the research engaged in that project will have normally certain applications. It means that we have to think about that. So all the conducted research were applied research, non-fundamental. If we are not able to write that on the project, we will not receive the funds. So the rules are very simple. But that's the way now to conduct research thanks to the European funds. So all these structures have been used for transportation applications. I will explain to you how we have done that. First, we have this mapping, this European job project have been entitled MAPIC project. It's mainly dedicated to the composite material. So we have used the fibrous material for developing very fast production composite material made with thermoplastic solutions. That was the aim of this project. And we have defined several solutions. One in the automotive applications, which is called the solution AutoMapic. The other was in the truck transportation application. It was called TruckMapic. And the third, but not the last one, was in the railway applications, and this is called RailMapic. They are the industrial partners, and at the beginning, the needs come from the industrial partners. We are not able to design what they want, so they ask us to say, okay, we would like to develop new kind of solutions. So the partners are Mecaplast, Volvo Truck, and Alstom. So these are the solutions we have developed with them. So to have a view on the AutoMapic solution, what is the idea of this kind of automotive brand, European brand, is in fact to replace, it's a black metal fitting, but okay, they have to replace a current steel solution by a new composite solutions. And as you can see, in every step, they want to reduce the weight of the solution. This is the main objective, the main purpose of developing that kind of solution. What we have done is to take part, to consider this part, which was an automotive oil pan made in a metallic part, and we try to replace it by a composite part. Also in the project, there are some colleagues aim to develop the modeling and simulation aspect of the project. So they help us to define the exact profile of the final part, the composite part. Of course, there are some adaptations because what you do with metallic solution, you can do not the same in composite and inversely. So thanks to this composite part, what we have done, this composite solution have been done thanks to, the idea was to develop a flat 3D warp interlock fabric. After that, this fabric was used only commingled yarns made of e-glass plus polypropylene. So one partner have been engaged for doing this application, industrial partners. And after, we have formed this 3D warp interlock structure into a 3D shape and using a thermocompression process. But using a thermocompression process means that you have to take care about several aspects. The fact that we have to fold make the folding, especially when there are two parts. But the most tricky thing and the most funny for us is the fact that sometimes you have to fold in a 3D part, like in the corner. 3 plans, it means a way to think differently. So, thanks to that, the idea was to take this flat structure, thermoplastic structure, to put inside a oven, infrared heating system, and then very fastly go to the mold and then pressed. So imagine that in the automotive production, this kind of way of doing this piece is very fast, only 10 seconds for producing that kind of structure. It means that during the forming, we are not waiting about the behavior of the fabric. It is very fast, very severe, so we have to take care about that. Okay, so taking into account that, we have designed our own machine for making the 3D warp interlock structure. This is one of the machines we have designed completely. And thanks to that, we have been able to make some pilot scale production. It's not a large scale, but pilot scale. But based on the main motions you can find on a Dobby machine, Dobby weaving machines. The type of 3D warp interlock was an angle with 6 layers based on a 2x2 twill. Thanks to that, we have been able to make some experiments, research on how this structure will behave during the forming process. So we have tested that with hemispherical or gousset to do that kind of experiments. We have inserted also sensor yarns and so on during the process, but I go quickly. What we are doing from our research part and point of view is the fact that we are measuring different parameters during this 3D forming. First, we are measuring the material drawing. The second was to measure the warp and weft sharing during this 3D process, very important, and especially when the structure is very thick. We have also checked that the thickness variations during this forming was not so disturbed. So is this thickness stay stable? And at the end, we have also checked the fact that there are no sliding, not high sliding between the external layers of the fabric. It means that how the slippage occurs during this 3D forming, especially when you are using in a fast production. So all these results are published in this reference mentioned just on in the Applied Composite Material Journal. So if you are interested about that, you can see that. And thanks to that, all this research, we have been able to develop one solution, and it works now for pilot scale production. And we have transferred to the industrial weaving partner that are able to design more pieces and put that in real production for the automotive suppliers. Okay, second part was the truck mapping solution with Volvo trucks. Again, we started with a metallic part, which is in fact a cabin truck seat reinforcement. This piece have been replaced by a composite solution, and if you can see where this actual metallic part is located, it's just located between the seat and the cabin floor of a truck driver. So this solution have to be replaced by a lighter solution, of course. And the second function was to be able to resist to a crash. And this was the second issue of this development. Very important. To take into account all these requirements, we have developed the composite solution, again using this 3D warp interlock structure, made also with commingled yarns, the same, and also using a thermocompression. But what you have to face and to think about is the fact that, okay, we are developing, we are replacing a metallic part by a composite part, but what about the joining? And this is one of the main research activities now were conducted. The bad thing now is the fact that everyone wants to replace metallic part by composite part, but if you not ensure the safe joining between the two, you will engage many efforts for nothing. So take care about that. So the main issue was to make a gluing solution, which is not the good one, but it works. And from an industrial point of view, it's very fast, and they are very skilled on that kind of joining applications. And also, we have some boltings because we have to screw with the seat to ensure that all this will work quite good during the crash. So very important to take into account that kind of idea. So as you can see on the picture, the final piece was placed in a cabin truck with a bolted seat, and this piece have been tested during a crash test. Sorry, the commandolians is coming now. Okay, so thanks to this solution, we have aimed to, the final aim was to have a weight reduction. Initially, the metallic part was 3.5 kilograms, and we succeed to reduce by more than half, 60% of the total weight. But okay, reducing the weight is one issue, but the second issue, very important, was to be successful during these crash tests. So these crash tests have been done, it works. And this final piece you can see on the top left, bottom left, it works. The final piece is safe. Except that we have, during the crash, we have to remove the we have to remove this piece to see if there are no damage. And you can see that when we are removing this piece, we have a certain amount of our piece that keep gluing on the cabin floor. So it was not, we have to work more to ensure a new type of joining. But this kind of solution is successful from the weight reduction and crash resistance. We have to figure out new joining solution. And third, other mapping solution was the well mapping. It's come from Alstom, also a metallic part. You can see across tubes, and these tubes, the joining is made with welding. And this kind of manufacturer, and I think that it's a well-known brand, they are very skilled in the joining with welding. It means that all their workers, all their team, people working in there, their workers are very skilled in the welding. But what to do if we replace that kind of metallic part, if they are not able to weld? That was the issue. That's why we try to develop a new composite solution where we avoid the welding. It means that thanks to the new solution, it is possible to integrate, from a weaving point of view, all the tubes and the plate together, and probably a new solution will be found.